Welcome to AI Podcast. I'm Ethan, and today we're unpacking a method that quietly reshaped how many language models handle word order. It's called RoFormer, short for Enhanced Transformer with Rotary Position Embedding. The idea sounds technical, but the takeaway is simple and practical.
Hey everyone, I'm Maya. Give me the conclusion first. What's the one-liner?
RoFormer replaces the usual way transformers track word order with a rotation trick called Rotary Position Embeddings. Instead of adding a position tag to each token, it rotates the query and key vectors by small angles tied to token positions. That makes attention naturally depend on relative distance, it plays nicely with long inputs, and it tends to train a bit faster. Gains are modest but steady, and the benefits grow as sequences get longer.
So the model learns distance and order without bolting on extra labels. Nice. Who led the work?
The paper is led by Jianlin with colleagues at Jianlin Technology in Shenzhen, published on arXiv in 2021.
Before we get into rotations, what problem are they fixing? Transformers are great with context, but they don't know order by themselves, right?
Exactly. Plain self-attention is position agnostic. Early models added absolute position signals, either fixed sinusoids or learned vectors. Later methods injected relative position information, often by adding biases to the attention computation. Those approaches work, but they're additive patches. They can be awkward for linear attention variants designed for very long sequences, and they don't naturally express the idea that distant tokens should matter a bit less.
So the gap is a position method that acts relative by default, scales to long inputs, and stays friendly to linear attention. Enter the rotation, I guess.
Right. RoFormer encodes position by rotating the query and key vectors in many tiny two-dimensional subspaces. Picture a set of compass needles inside the vector space. Move one token forward, the needles turn a bit. Move two tokens, they turn twice as far. When the model compares two tokens, the dot product reflects the difference between their angles, which is their relative distance. Rotations preserve vector length, are numerically stable, and with the usual frequency schedule, they produce a gentle decay for far-apart tokens. Because the encoding is multiplicative rather than additive, it composes cleanly with linear attention techniques.
That mental image helps. How did they test the idea?
They ran a set of experiments across common and long context settings. First, machine translation on the WMT14 English-German benchmark using a transformer-based model with RoPE swapped in. Second, BERT-style masked language modeling, pre-training, comparing training dynamics with and without RoPE, followed by fine-tuning on selected glue tasks. Third, a long sequence is set up with a linear attention variant called Performer on the NWIC8 dataset. And finally, long document evaluation on Chinese legal case matching, where they could raise the input length beyond the usual cutoff.
And the results?
On translation, RoFormer edged out the baseline under matched settings. During pre-training, the RoPE version converged faster, meaning the loss dropped more quickly with the same setup. Glue results were mixed. Improvements showed up more on pairwise similarity tasks, while some short single-sentence tasks were comparable or a bit lower. With Performer on NWIC8, training was smoother and reached lower loss when RoPE was used. On the Chinese legal case matching benchmark, the advantage became clearer as the maximum input length increased. In short, the longer the sequence, the bigger the payoff.
That lines up with his design. Can you give a plain language math intuition without diving into formulas?
Think of each token vector as many small 2D slices. Position tells each slice to turn by a certain angle. Queries and keys both turn. Attention then measures how their directions align after turning. Because angles add, the score depends on how far apart two tokens are. Because rotations are orthogonal, you don't distort magnitudes. And because different slices turn at different rates, you get a rich pattern that captures local and longer range structure.
What about engineering trade-offs? Is it heavy to add?
It's lightweight. You apply the rotation to queries and keys right before attention. There's no extra embedding table, and it doesn't change the network shape. Rotations are cheap, they preserve norms, and they avoid the algebraic conflicts that additive relative biases can introduce for linear attention methods.
You mentioned mixed glue outcomes. Should that worry people?
I'd read it as task sensitivity. Glue has several short, sentence-level classification tasks. Rotary embeddings are most helpful when relative distance and longer context structure matter. On short inputs where lexical cues dominate, the benefit can shrink or even flip. That said, the training dynamics gains were consistent. In the long document, results match the hypothesis.
How big were the models? Are we talking giant-scale training?
No, the experiments were moderate by today's standards, which is useful for practicality, but also means small deltas can depend on hyperparameters and random seeds. Larger controlled comparisons would be valuable for a fuller picture.
Is the method accessible now? Can people try it without reinventing the wheel?
Yes, rotary position embeddings are widely available in open-source libraries, and many modern models use them by default. If you're stretching context windows or experimenting with linear attention, it's an easy switch to try.
Let's wrap with a compact recap.
RoFormer introduces rotary position embeddings. Instead of adding position vectors, it rotates queries and keys by angles tied to positions, making attention sensitive to relative distance in a stable, norm-preserving way. Experiments show steady improvements in translation, faster pre-training, and clearer gains on long document tasks, with good compatibility for linear attention models. Results on short, simple classification are mixed, and the studies were mid-scale, so there's room for larger follow-ups. But the method is simple, elegant, and practical.
And if you want a picture to remember it by, think of a row of compass needles turning as words move through a sentence. Nearby needles line up, far ones drift, and that shows up directly in attention. Thanks for listening to AI Podcast. We'll be back with more careful looks at ideas that change how we build models.